Intensity versus distance from the center. Monochromatic light of wavelength 620 nanometers from a distant source passes through a slit 0.45 millimeters wide. The diffraction pattern is observed on a screen 3 meters from the slit. In terms of the intensity I sub 0 at the peak of the central maximum, what is the intensity of the light at the screen the following distances from the center of the central maximum: 1 millimeters, 3 millimeters, and 5 millimeters. We have to recall the intensity distribution for single slit diffraction. So the intensity in single slit diffraction is I0 sine phi over phi squared, where phi is pi a sine theta divided by lambda, and here we are given a, the slit width 0.45 millimeters. We're given a distance to the screen 3 meters, and we're given a wavelength of 620 nanometers. So if you look at distances on the screen, delta y, these are equal to L times tangent theta, which is approximately equal to L times theta for small angle approximation, and sine theta is also approximately equal to theta. With that, we have phi given by pi a delta y divided by lambda L. So tangent theta is equal to sine theta, which is delta y over L. So we substitute that here. So we have pi a over lambda delta y over L. Okay, so basically we are looking at this delta y from the center of the central maximum at an angular displacement theta with respect to the central axis. So we have the slit width a and the viewing screen a distance L away. Okay, so with the small angle approximation, we have phi is pi a delta y over lambda L, I0 is sine phi over phi, I equals I0 sine phi over phi squared. So the intensity distribution is given as I equals I0. Now we have sine pi a delta y over lambda L divided by phi, which is pi a delta y over lambda L parentheses squared. So this gives us an intensity. So this lambda L will go upstairs, and with the square it becomes lambda square L square divided by pi square a square delta y square I0 sine square pi a delta y over lambda L. So this is basically the formula we will use to calculate the intensity at each location. Or we can say that I is equal to I0 over phi squared sine squared phi. Okay, so let's go to part A of the problem. Part A is asking us the 1 millimeter separation. So for 1 millimeter separation, what is the phase phi 1? It will be pi A is 0.45 millimeters. Delta y, in part A, we're looking at 1 millimeter distance, divided by 620 times 10 to minus 9 meters, and L is 3 meters. So we obtain phi is equal to 0.76 radians. Corresponding intensity at this location, I1, will be I0 divided by 0.76 squared, and then we have sine squared 0.76 radians, and this gives us an intensity I1 equals 0.822 I0. In part B, we're interested in what happens at 3 millimeters from the screen. So as you can see, when I change this 1 to 3 millimeters, basically I'm talking about 3 times phi 1. So phi 3 is just 3 times phi 1. And therefore phi 3 is 2.28 radians. The corresponding intensity I3 is I0 divided by 2.28 squared, and sine squared 2.28 radians. This gives us an intensity of 0.111 I0. And in part C, we want to know what happens at 5 millimeters from the center. At 5 millimeters, we have 5 times phi 1 as our phase here. So phi 5 is 3.8 radians. The corresponding intensity is I0 divided by 3.8 squared, sine squared 3.8 radians, and this gives us an intensity of 0.0259 I0. Okay, so in this problem we're looking at intensity as a function of distance from the center on the screen. We have single slit diffraction, monochromatic light, which goes through a slit opening 0.45 millimeters. The diffraction pattern is observed at a distance 3 meters from the slit, and we want to know in terms of the intensity at the central maximum I0, the intensity of light at the screen in 3 different distances. So when theta is equal to 0, phi is equal to 0, we have the sinc function giving us sine phi over phi. In that limit becomes 1, so we have a maximum intensity I0. Now when we go away from the center, it will decrease as I0 sine phi over phi squared, where phi is pi a sine theta over lambda. It's basically phi divided by pi is a sine theta divided by lambda. So you can see here path difference divided by lambda is phase difference divided by pi. So delta y on the screen is tangent L times tangent theta, or tangent theta is delta y over L. For small angles we have sine theta and tangent theta equal. So tangent theta is delta y over L. Sine theta is approximately delta y over L. So we substitute that here, and we have I0 sine phi sine square phi over phi square, where phi is pi a delta y over lambda L. So this is basically what we are using. So pi A delta y, pi A delta y over lambda L is for phi 1. This delta y is 1 millimeters, phi 3 is 3 millimeters, so it's 3 times phi 1. Phi 5 is 5 times phi 1, 5 millimeters, so in part C. So we substitute that and calculate phi, and sine square phi over phi square gives us the factor of I0. So 0.822 I0, 0.111 I0, and 0.0259 I0.